Hello everybody, this is the second video in the series of lectures under RF Microelectronics. In the last class we saw about tuned circuits. So this was the tuned circuit which we discussed in the last class, where we wanted an amplifier which amplifies only the required signal, and then we used an PMOS. It is essentially an LC circuit. Okay, so the omega is equal to 1 by root LC will decide what is the resonant frequency, and only that particular frequency will be amplified, and that L is fixed out here, and we, for instead of C, we used a variable PMOS. So this is what we learned in the last class, right? So all practical inductors which are implemented on VLSI chip with series with a loop like this, right? We take a metal and keep making loops to realize this inductor. It will have a series resistance also, because these metal will have some resistance, right? So depending on the resistivity, so this inductor will have a series resistance, and that series resistance degrades the quality factor of an inductor. So that is a problem when we are having an on-chip spiral inductor. That series resistance, we saw that it is going to degrade the quality factor. Okay, if you see here the bandwidth, that selectivity right aspect is degraded out, or the quality factor is, okay, the ability to reject the unwanted frequency, okay, that is degraded because it's become very wide, right? This, so that was the drawback. Okay, another drawback with inductors is it occupies a lot of silicon area. So this is one of my work. If you see here, in this much area there are around 400 odd transistors, okay, but this is a single 1 nano Henry inductor. So you see how much space it's taking out here, right? This is 0.5 nano Henry inductor. So the inductors occupy a lot of space. Okay, so there are two drawbacks in a RF microelectronic tuned circuit which employs spiral inductors. Okay, the one is it consumes a lot of silicon space, and second, the quality factor. Okay, the Q is bad, right? So now we have something known as active inductor. Okay, so instead of having an LC like this, okay, like this together, this LC tank circuit can be implemented using an active inductor. Okay, so this is the circuit. Okay, so if you see here, the input is given, this entire thing acts like a tank circuit. So this is the small signal equivalent circuit out here, and probably there has to be a ground also out here. Okay, so let me do that, right? Because there is a DC here, right? So so there will be, so if you see here, this is equivalent to this tanks, an RLC parallel network. Okay, and if I apply a test voltage out here, VI, and if I compute the I, okay, the current, right? So V in divided by I in, if I write the equations, I will get Z in. Okay, now if I put all the real values, okay, if I segregate all the real values, so I'll get this. Okay, so this is the real part. Okay, and this is the capacitance. This capacitance will be given by this. Okay, the inductance will be given, this inductance will be given by this value, and this series resistance will be given by this, and the quality factor will be given by this. Okay, so this circuit, and if I look from here, it would act like an tank circuit. Okay, so this is the equivalent tank circuit, and if I write the equations, okay, I just have to write V in, I apply a test voltage, and try to find the current equation, and then if I do V in by I in, I will get Z in. Okay, now that parameters, whatever I get Z in, if I try to map it to this equivalent circuit, so these are the values which I get. So if you see here, capacitance and C, this C equivalent is given by the capacitance of this transistor, right? And the inductor, this L is given by CGS and the GM of these two transistors. Okay, GM of these two transistors. right? GM1 and GM2, okay, these two transistors, right? And so the and even the quality factor is given by this. Now from here, so how can we tune that? We can simply tune that by varying, right? So we know that tuning frequency is given by 1 by root omega LC. Okay, C gets fixed by the MOS capacitance, whatever it is here, whatever transistor we use. So C gets fixed. L is a function of GM1 and GM2. So by changing the currents out here, I1 and I2, I can tune the circuit to various resonant frequencies. Okay, so I can get so. I think this is a duplicate slide. So we will try to do this in Cadence, and we will see how to tune this to various operating frequencies. So this is the circuit. This is, I am going to replace here in this circuit this tank circuit with this circuit. And I am going to change the values of I1 and I2 and try to tune the circuit to various frequencies, like we did this here, right? We were able to tune this, the circuit for amplifying only the desired frequency. That is what we are going to try to do with the active inductor also. So let me show the simulations in Cadence. Okay, so this is the first circuit which we are going to discuss now. This has been, I have targeted 30 megahertz to 50 megahertz tuning range. So this is an CS amplifier. Okay, so there is an a constant current source PMOS load out here. So VDD is given here, and a fixed voltage is given to the gate of the PMOS. So this is a constant current load. This is an NMOS. So this NMOS has been biased by resistance, these two resistance 50K and 60K, and I'm giving an input signal. So the input signal AC magnitude is 1 volt. So first I am going to do an AC analysis, and then later on I am going to do a transient analysis also. In the transient analysis, the input voltage which I have given is 10 milli, and 31.62 megahertz is the frequency which I have given here. Okay, so that would come in the transient analysis. But first let's focus on the AC analysis. In this tank circuit, okay, we saw in the circuit there's a VG voltage was required here, bias voltage. So instead of having an VG voltage here, I have given an DC current out here and a resistance out here to generate the DC voltage out here. And these two current I1 and I2, I am going to take various combinations and see whether the resonant frequency of this particular tank circuit changes or not. Okay, so I am going to take some variation of I1 and I2 and see that the resonant frequency changes, and that's how the tuning is done. Okay, that's what we are going to do the analysis. Now see, 30 megahertz and 50 megahertz, it's slightly very on the lower range for an active inductor. So I have taken these transistors very large. So if you see, the width is 500 micro. This is also 500 micro, and the length is 450 nano, although this is 45 nanometer technology. So I have taken huge transistors so that the capacitance is large, which will result in a resonant frequency in 30 to 50 megahertz range. Okay, so I am going to launch, let me save this and launch AD Explorer. Okay, create a new. Okay, okay, yes, okay, analysis, choose. Okay, I'm going to do an AC analysis, right? And I'm going to sweep it from 1 megahertz to 1 gigahertz frequency, and let me have an logarithmic sweep out here, right? And let me take 100. So a good number of points, let me take it for accuracy purpose. So this is the AC analysis which I have set now. Okay, variables, copy from the cell view. So there are 3 variables. So I3, I said we are not going to change we are just using that for biasing. So I give it as 550 micro. I1 I am going to change this. Okay, I am going to set some two different values and see how it is going to change. So let me give I1 from 7 micro to 12 micro, and number of steps 2. So it would take 7 micro and 12 micro. Okay, you can give any values. Okay, that's and for I2 I am going to take again from 2. So I am giving 2 values for I1 and I am giving 2 values for I2. So it should do a total 2 into 2, 4 different combinations. Okay, simulation for 4 different combinations. Okay, so that has been done, and we also have to do some output setups, right? So output to be plotted on design. This is AC analysis. So we are going to see AC magnitude, and here we have given as only 1. So obviously for the frequency at which it's resonating, it should amplify. So let's see what's happening. So there are 4 different simulations now running. So yeah, first it would come as net listing finished. Okay, and then the simulation would start. So all the net listing is finished and simulation finished, and then the plottings would start. Okay, so all the plot. Now if you see here, these are the plots. Okay, so if I click on this, okay, for 7 micro and 10 micro combination I1 I2, I am having 31.62 megahertz, correct? And if you see here, and for the like 4 different combinations, and here I am having 47.8 megahertz. Okay, here also these are different values, 35 megahertz and 41 megahertz. So you see here the for different I1 I2 the circuit tuning is different, right? The resonant frequency is different. So I am able to tune this circuit for different frequencies in the range of 30 to 50 megahertz. Okay, and the range is generally from more than 2.5 to around 3.5, right? So it's a good. Okay, so the signal is getting amplified 2 to 3 times. Okay, that is there, more than 2, in fact 2.5 to 3.5 times it is getting magnified. Only the desired frequency is getting magnified, and the Q is also much better, much better Q. You would get quality factor, very sharp small bandwidth. Okay, sharp bandwidth as compared to the normal inductors. Okay, spiral inductors. So these are the advantages. So these are the 4. Now I want to be sure that okay, in AC plot what I am getting, that is what is happening in the transient also. So let me close this, and let me do a transient analysis also. So analysis, choose. Okay, now I'm going to do an transient. Let me do a moderate one, and 0.1 micro. So I am giving only one particular frequency in the transient, right? Input, I am not changing the input. So for one particular combination, it would be amplified maximum, and for the other combinations of I1 and I2, it doesn't represent that particular tuning frequency, and hence it will be attenuated. So for the first combination we saw in the AC analysis, it was 31.2 megahertz, 6 megahertz or something like that, right? So you will see that for that particular, and I have given the same input, so that is being amplified here, right? So if I put a marker A and B, yeah. So I am getting around 61 millivolt peak to peak. Okay, so input was 10 millivolt peak to peak. So obviously more than 3 is the gain. Okay, so this is how now it is verified in the transient analysis also. Okay, so now let's try to modify this circuit for slightly higher frequency. Now to get a much higher frequency, so the first thing which I did was, so So I have decreased the width and the length of this transistor. So I have taken just a 50 micro now, okay, and then I have brought down the length also to 45 nanometer for both these transistors. Okay, so the width is just 50 micro and 45 nano, 50 micro and 40 nano. So the effective capacitance out here is now reduced. Okay, and because of which the frequency will be much higher. Okay, the resonant frequency. Okay, and this is the same setup. Okay, only what are the changes we will see. So here again 50 micro, that was the bias current just given to generate the bias voltage. Here again I have taken 8 micro to 12 micro. Okay, so two different values. Okay, and for I2 I have taken 6 micro to 10 micro. Okay, so I have just so if you see the circuit out here, I am changing I1 and I2 like in the previous case also I took 50 micro to give to that just to generate the bias voltage. These two will give the different two values I have taken. So 2 into 2, 4 different I1 I2 combinations will give me 4 resonant frequencies. Okay, as compared to the previous circuit, the size of these transistors are much lesser. Okay, so now if I do a simulation out here, you can give, I have taken 2, you can give a more number of combinations, and you can do it mathematically. You can try to find out what are the currents required for a for your tuning, but simulations through simulations it is much easier. So if you see here, this is like 3.5, the gain is around 3.2. Okay, for this is 372 megahertz. Okay, whereas here for a different set of I1 I2 combinations it is going up to 576 megahertz, right? So you for I1 I2 other frequencies also are available here. This is 502 megahertz, and this is 408 megahertz. So somewhere from 350 to 500 megahertz range frequencies, by changing these currents, it's available here. So if I want to go still further ahead, right, of our frequency, say if I want to do an simulation of for 1 gigahertz. Okay, I want tuning frequencies close to 1 gigahertz. So let me keep this as it is. Okay, let me just change I2 and see. So you can do that, right? So I2 instead of 6, let me take much higher current, like 20 and say 22. Okay, so I am taking that. So this is how you can do, right? So you can decide the values of I1 and I2 for your design. Only thing is the I1 and I2 values. This circuit is very sensitive to the tuning currents. Okay, so it is better to take I1 and I2 from a band gap reference voltage, right? So this is 677 megahertz, and this is around 853 megahertz, right? It's coming close to 1 gigahertz now, right? The 7. So you see it's gone up to 853 megahertz. Maybe if I increase further, it can go up to let's if you want to see that, we can try and do that. Right, so let me just instead of 12, let me take this as 14, and here instead of 22 I take as 24. Okay, and then I do a run. So now around 800 megahertz we got for those combinations. I'm just trying to further improve, see if we are able to get around 1 gigahertz. Not sure. Let's see what's going to come up. Right. Okay. So here, yes. Right. So it is like okay. It is coming around close to 1 megahertz. Okay, 914. So if you see, as I'm keep increasing, this also might have gone up, 693 to 914. Right, you can do that. So it's possible to get close to 1 gigahertz also. So let's try even that one. For one last try, we can do that. Right. Let me change this from 12 to 16. Okay, and this from 22 to say 28. Okay, and then I run a simulation. It would be probably a little difficult actually trying to do a mathematical analysis and trying to find the currents. But since the tool gives us this option of doing a parametric analysis, so it's a better option, right? So you can see here that it's reached 1 gigahertz, right? 1.014 gigahertz for this particular range, right? So that's the how you can that's how you can select the values of I1 and I2 through simulations, right, by giving this appropriate, and then find what is the range. Okay, so depending on what is the range you want, right, with that, within that range, and how to tune, so those I1 I2 values can be found out using simulations. Okay, thanks a lot. We'll stop it here. In the next class, probably I will talk about LNA design and how to do an S parameter analysis. Thank you.